for giving me this opportunity to talk about my work. Also to Arti for chairing the session. So I will be talking about Fock space fragmentation and I will define what do I mean by Fock space fragmentation in quenches. Before I speak, let me also thank my collaborators. So there are many. So in particular, Ishita, she is a PhD student at IIT Bombay and most of the work is done by her. Good. So just to set the stage, let me start and think about systems which are closed systems, as we were discussing already, and these systems are energy conserving. Yeah? So this is the two main important ingredient in my talk, and throughout the talk, this will be kept fixed. Yeah? So energy conservation, closed system. Now, we know more or less all of us know how a system of such thermalizes. When we say that a system of such thermalizes, we precisely mean local observable thermalizes. And at very long time, under a time evolution, let's say starting from a quench, which is a pure system, the system thermalizes. And if you look at the long time average, what happens is that you can write down such a small thing, ignoring some other term because of the long time average. And what you get is actually a term which is a matrix element of this local observables and a coefficient. So the coefficient knows about the initial state, it doesn't go away, it's a closed system. So the memory is over here, whereas over here is a matrix element of the local observable, and that local observable is actually a smooth function of energy. Okay, so that's the assumption of a hypothesis, which is we call Eigenstadt thermalization hypothesis. Under this condition, what happens is that this value at very long time of a local observable goes to its microcanonical value. So what is important here that there is an energy window within which this local observable is independent of energy, and within that window it gets its microcanonical value. Okay, so that's kind of the zeroth order explanation of this thing, and we have seen it. Yeah, so there are many examples now. For instance, this is an example of a numerical simulation of a ladder. What is plotted over here is a rung operator of this 4 thing. It's a Bose-Hubbard model, long time back. So this is the energy, that's the operator value itself. This is a scenario when there is no interaction, a model is integrable, you see a lot of fluctuations. The red line is essentially the line of microcanonical value of that operator. Now if you look at over here, so this is the energy window and the operator value almost is very smooth in a sense that this is approaching the red line, but still there are fluctuations, and this fluctuation goes as 1 over the square root of the dimension of the Hilbert space. Good. So that's kind of saying that this operator is thermalizing for this model, whereas for non-interacting model that operator is not thermalizing, the model is integrable, there are a lot of integrals of motion. So that's a numerical simulation. This is a example of an experiment in a cold atom experiment 10 years back, almost, no, a long time back, 2012. And what has been shown that this is the occupation of an odd site where initially in the odd site there was no particle. Okay, so you start a quench, even odd quench in a sense that the even sites are all occupied, odd sites are not occupied, and you monitor under the time evolution how the occupation changes. What you see over here is that the occupation increases and eventually the oscillation goes down and it becomes almost flat. And that number is essentially the number of a microcanonical situation. So that's the idea that against the thermalization hypothesis, and I want to propose this or want to try to tell you that there is a different way of look at it, is that it means that there is an efficient exploration of some energy space. So that's one way to think about it. But there are other examples, so that can be broken. For instance, this is a classic example which already Krishnanduda was mentioning. It's a PXP model where there are states which are atypical states. And if your initial state has a large overlap with these atypical states, the system will take a much longer time to thermalize because it takes longer time to decay into this continuum or essentially explore this Hilbert space. Yeah? So that part of the energy space is not given by these states. Experiments are done again. So this is an experiment on the Rydberg blockade, which you all know now by now. Misha Lukin group, and what you see is the domain world density for a long time, at least for the experimentally long time. It's a system independent oscillations which persist. The fact that there is this oscillation is essentially telling you that there is some sort of emergent or scarce states actually over here. Eventually it decays down. The reason eventually it decays down is because the systems are not perfectly closed. Yeah, so there is a kind of a leakage channel, and that allows you to have this decay.
What do you mean by atypical? What is free?
By atypical, I mean there are states which has far away from this continuum of energy eigenstates, which has low entanglement.
Sorry, no,
That's the overlap of the initial state with respect to the energy eigenstates, and the initial state has a large overlap with those states. Those states has low entanglement, area law, which is atypical because usually you expect in a non-integrable model a volume law entanglement. I don't know. Okay, let me go ahead and tell you a different story. A different story is that there is a different way to think about thermalization, which is from the Fock space perspective. Again, I'm thinking about a scenario when I'm looking at occupation basis or usually the computational basis. In that basis, again, we look at the wave functions. So I'm moving from operator thermalization to now wave function, going from energy space to the computational basis space. Now, what you see over here is again a time evolution of a wave function. These are the coefficients, and typically what one looks at is actually the some sort of entropy, which is the participation entropy, tells you how the wave function kind of explored the full Fock space. Or IPR, inverse participation ratio, inverse of that tells you again how big the wave function occupies the Hilbert space of the Fock space. Good. So, what is the claim? If a system thermalizes, these coefficients will obey our RMT, the random matrix theory, which is essentially a Porter-Thomas distribution. So, it will essentially be random, and from there you can show that the effective volume typically goes as the dimension of the Hilbert space, d being the dimension of the Hilbert space, and the entropy becomes log of this dimension. If it is 2 to the power L, it is essentially a volume law. It is a participation entropy, not the bipartite one. Good. So, that is kind of the thermalization in the many body configuration space. Again, it has been checked very well. So, essentially last year it has been shown even analytically possible. So, this is a model which is a mixed field Ising model. So, you know the transverse field Ising model with a longitudinal field. You tune it in such a way that it goes into this thing called dual unitary. Yeah, that dual unitary point is exactly solvable. So, if you solve it within few time steps, so this is a Floquet system. So, within a few time steps, this blue are this P alphas. So, this is the definition of a Porter-Thomas distribution. So, this P alpha is this blue and the red is the analytical calculation, which clearly shows that it goes there within very few time steps and the system thermalizes efficiently. Good. So, what am I talking about? So, what am I talking about is that a scenario can also appear where this configuration can be blocked. Yeah? So, this already given an example in the first talk by Krishnendra that if you have a strong external drive with a large amplitude, you can stop that efficient exploration of the configuration space. If you have certain kinetic constant, you can again thermalization can be stopped. Obviously, there is strong Hilbert space fragmentation that can appear because of certain symmetries, for instance, dipole conservation in the PXP model, and again thermalization can be restricted in the same way in the energy space as well as in this configuration space, where this log d and the effective d scaling will be stopped. Yeah? We know that even with experiments. So, this is a cold atom experiment from last 3 years back. What has been done is you prepare a cold atom and put a strong field. Yeah? It is a tilted field, it is called Stark field. In this Stark field, what happens is that at very large Stark field, which is much bigger than the interaction strength and the hopping amplitude, the Hamiltonian breaks down. You can do a perturbation theory, breaks down into sectors. Yeah, and this is essentially the fragmentation that has been discussed previously. Emergent dipole conservation happens, and because of this dipole conservation, the system does not thermalize. Okay. So, this is fall into one of this class, and what you see.
Second order, right?
It is up to second order, up to fourth order one can do still calculate, but these are transients. It will thermalize, everything will thermalize eventually. Yeah. So, this is transient times. Again, it's what you look at is essentially the even odd occupations and how it changes. This even odd occupation. This is the imbalance, and what you see one imbalance means a perfect unoccupation of even and odd sites, whereas going finite essentially implies that the system is, at least for the transient, is not thermalizing. Good. So, let me just quickly summarize what I have been talking about. What I wanted to tell you that we are talking about non-integrable systems. This non-integrable systems lives in this really large Hilbert space, which is exponentially large in system size. So if you start from one point in this Hilbert space, a wave function has infinitely many paths to leave and essentially explore the full Hilbert space. However, there are certain things like Hilbert space fragmentation or let's say kinetic constraint, strong Floquet drive can restrict, or atypical states like scars can restrict thermalization or at least even transiently. Okay, so that's the basic thing that I wanted to mention to you. And what I want to tell you in the last couple of minutes is the following: the disorder gives another mechanism. It's a separate mechanism. Again, is a transient mechanism that also will give you a Fock space fragmentation. However, it's a geometric fragmentation. So let me just mention a couple of things here. So this is a geometry of the Fock space that it will essentially fragment. It's not an exact fragmentation that one usually see in this dipole conservation or kinetic constraint models. So it's a depends on the initial state, which is important because I told you that ETH also has important information about initial state. There is a concept of energy shell. So this is an energy shell that I already mentioned, within which the system efficiently explore all the energies. So that's essentially the microcanonical window. And then obviously it's a geometry because, and that's why it's a classical in nature. So there is no quantum mechanics involved in whatever I'm going to talk about in the next couple of slides. Okay, good. If you have any questions, please you can ask me at this point. If not, okay, great. So let me just be more specific. So I will be talking about a very simple model. So this is a 1D Heisenberg, 1D Hubbard model, spinless Hubbard model with nearest neighbor interaction with on-site disorder. So this disorder is chosen randomly between minus W to plus W, and I have put everything in 1. So that's the only scale left in this problem. Yeah. So interaction is 1, hopping is 1. So this is the disorder. And if you look at this model and if you do this quench experiment that already the experimentalist does, what you see over here is the following. So this is you can choose one disorder value which is close to 1 again, and you do different configurations of disorder. What you observe that this imbalance sometimes goes to 0. So this is one sample where it starts from 1, it goes to 0. You start from, in this specific case, from a null state. So you start from 1 and you go to 0, but then there are several samples which does not go to 0, at least within, again, the time scale that one can simulate. So this is a computational simulation, which is inverse hopping is around 10 to the power 4 or so, and it does not. Eventually we hope that this also, eventually it will go to 0. But the question that I'm asking, within this transient time, what is the mechanism that allows it to be finite and allows it to go to 0? Okay. Good. So even more specific. So what I will talk about is essentially mostly the occupation basis. So this occupation basis, if you know that this is this 2 to the power L number of points, and I am going to look at this 2 to the power L number of points. Each of these points has some energy that comes from the diagonal part of the Hamiltonian, and this thing is essentially the density and the interaction strength. So this is the energy of each of these occupation bases. Between this occupation basis, there is a hopping, and that hopping is given by the t, which is order 1. Yeah, it's not random; it's just order 1 number. This is this microcanonical shell that I am talking about. So that is important for the ETH to happen, but here also. So we will define certain shell, which is the variance of the initial state onto this Hamiltonian, and then what I am going to look at is actually how many occupation basis falls into this energy shell. Okay, so again, this is just the coloring of that thing. So this is this occupation basis projected in this 2D space, and I have arranged it in the following way, so that the initial state is the null state, and then every time I hop, there is a 1 hop distance away, you will find some states, and these are these states. So it is arranged in what is called Hamming distance or the spin flip distance away. All these points are connected to each other in certain ways. They are extensive connectivity. I just removed it for the moment for this clarification, just for simplicity. I'll bring back that. And what you see over here is that these red points are essentially those points that lives in this microcanonical window. Remember ETH? So this ETH is essentially an exploration of this microcanonical window and an exploration in that sense of these red points. Okay. So there are certain scaling. I skip it for the interest of time. What I am going to show you that if you think about it and if you just count this number, there is almost an exact correlation with the imbalance that I already mentioned to you, which is quantum mechanical. Over here is just counting numbers. Okay, so here is the thing. So it's a number of red points that is over here normalized with respect to the dimension of the Hilbert space. So it's 70% space fillings, if you wish, and in that sense, imbalance becomes very, very small. So as you can think about that, there are many paths for the initial wave packet, which starts from the null state to move. Yeah, so that's the first thing. Whereas over here is it's 25% space fillings, and what you see over here that the imbalance is quite finite, and that part is non-thermalizing. Yeah? So the thing is that if there are many number of points or many red points at this point qualitatively, the system is thermalizing. If it is not, system is not thermalizing. However, there are counter examples. So this is a number which is more than 25%, but has much more imbalance than that. Yeah? What am I missing? So this is a counter example to the previous two intuition, and what am I missing is actually that they are connected to each other. It's not that they are individual points living in this high dimensional space, they are connected to each other through this hopping thing that I've already talked about. And that if you bring in, things become more interesting. So here is the connectivity of that red dots. Yeah, so this is within this microcanonical window, and I'm just connecting them of their of this. Obviously, I'm not connecting them, but they are also connected eventually. Yeah, so even the white dots are connected eventually. What you see over here that this 70% has a huge connectivity. Essentially, it forms a big cluster in this space filling geometry, and then the imbalance is very small. Whereas over here, this 30% sample is actually, even though it has more red dots, the connectivity is fractured in a way which is very interesting, that these 4 dots are connected to each other, whereas there is a big chunk of these points which is separated from that 4 dots. Yeah.
Sorry for the interruption. I mean, if I monitor the IPR,
Yes.
the inverse participation ratio.
Yes.
So for the left versus for the right,
Yes.
I will always find the state at time t
Yes.
to be having less IPR.
Yes. Yes. So what will happen? There is a correlation between the IPR, not directly IPR, but something called the D1, which is the IPR divided by the usual scaling, that number with the imbalance. I will not show it, but it's there. Yes. But I will show some correlation at least. So for instance, first of all, the time evolution itself. So if you look at the time evolution of that wave packet, so you start from here and you evolve over time. So this is time, and this is essentially the wave function square. So the density of the wave function on the many-body Fock space. And what you monitor over here, these big dots, is how much it is there. Yeah, it measured some measure. And what can we notice that there is a significant pattern emerges. So there are kind of an oscillation over here. This one comes back over here, this one comes back over there, that one comes back over here in certain time scales. And this oscillation, so the wave packet is essentially moving in this small fracture. It's not yet leaked to the bigger structure, and that shows up even in the imbalance. So the imbalance over here has certain oscillations, and these oscillations can be found over here as well. Okay. So there is a one-to-one correlation. Not only that, you can essentially look at all the imbalance that you can do. So there are thousands and thousands of samples. What has been plotted over here is essentially what is the biggest cluster, not in that in the red dot structure. So essentially the connected cluster with the initial state, and then it is plotted as a function of the final imbalance. Yeah. So 0 means the system is thermalizing, whereas very finite imbalance will be over here. Always null state. Precisely. So it is for 2 different system size. So let's look at the largest one, 20, and you see that it is not random numbers. So over here, when the system is becoming ergodic or thermalizing, the connectivity increases to 1. So essentially, it is space filling, and it's, all the points are connected to each other, and the fragmentation becomes increasingly large. Even becomes very small number when the saturation is also very large. Yeah? So there is a kind of a diagonal correlation, and it's quite evident. Good. So let me just quickly summarize what I have talked about. So what I talked about, that there is 2 ingredients, 2 important effects. One is how many number of dots are over here and how well they are connected with each other. If we know this, there is a kind of an understanding of how the imbalance is behaving. Therefore, each disorder configuration, each of these energies are different, connectivity is different, and the number of dots are different, and that's why there can be some samples which are non-ergodic, there can be some samples which are very ergodic. Yeah, so that's the, yeah. Yes, please, Sohan.
This is only for short time.
These are all but short in the unit of t is 10 to the is a thousands.
Including virtual hoppings, for example, so those will come into play later.
Absolutely. So these are all classical geometric effect. I am missing two important ingredients, that the particle can go out of this red thing and come back. This is called loops, and these loops can interfere with each other. Yeah, they are things. But these are all qualitative sample to sample behavior. What I want to talk about is the average quantity also, because that's kind of just a couple of samples. And if I look at the average property, that shows very interesting things. So for instance, this is the average size of this connected cluster as a function of strength of disorder for different system sizes. And what you see over here, that there is a crossover. Yeah. So for small disorder, let's say order 1, there is the connected cluster is 1. So it means that this is nice thermalizing properties. Whereas with increasing disorder, it becomes really small. That's essentially meaning that only the null state survives and the system will not thermalize. Yeah. The variance of that number also shows certain behavior, similar behavior. Exactly where the crossover happens, it peaks and it moves. And what we now want to understand, how it moves and what is the meaning of this moving. Yeah. So again, I have very small system sizes going from only 12 to 24, and I am claiming that this movement is logarithmically slow in system size. That's okay. Important point to note already at this point, that my connected cluster is a bounded quantity, therefore variance is also a bounded quantity. Yeah, and that's very important, because there will be never a point, any sample, it will go above 1, because it's normalized in that particular way. Yeah. So if that is the case, the variance is bounded, and this point I will come back. That will give us, because if it is always log L, it means there is no finite crossover anymore in the L goes to infinity limit. Yeah. So because log L will always goes on, but this mere fact that these systems are bounded, sorry, this quantity is bounded quantity, it allows me to kind of get a bound on that. Yeah. And the way to get the bound on it is to look at such a plot. So what I do over here is essentially plotting the variance over the mean, and it collapses with some scaling, only one variable, which is the L scaling. From here you can calculate a number which is the L star, around which this log L flow will stop. Yeah, because the variance cannot keep on growing, and that's this plot. So essentially it can move. So this is the mean of this variance. So this is this point. These are left with and the right point of this variance. They all move. This is a logarithmic scale, and you can estimate L star where it will stop. Yeah, so there will be a transition, a fragmentation or a geometrical transition in the many-body Fock space of that energy shell around the disorder 8, and that's a thermodynamic statement. Good. So can we understand a little bit more? Yeah, understanding a little bit more is a bit difficult because of this correlation that the Hilbert space fragmentation has. So for instance, this is essentially the Hamiltonian in the Fock space, where these are the basis states, the occupation basis states. I have this hopping T, and then there is this epsilon beta, which are correlated numbers. Why they are correlated is easy, because I start with L random number and I am promoting it to 2 to the power L numbers. So there has to be some combination of those to make it correlated. So that's the correlated variables. And also I have extensivity of the graph. Yeah, so the graph is L extensive. So each point is roughly on an average connected to L other points. So this is extensive graph with correlated variable at each node. Yeah, so that's a difficult problem, and that's the many-body Fock space problem. So you can simplify it by saying, okay, let me keep one of this extensivity, but let's forget about the correlation. So if you forget about the correlation, you can take those numbers to be a random variable. Yeah, so completely random variable, and that model, essentially a model which is known as quantum random energy model. Yeah, so that's a model with the extensivity but without correlation, becomes much easier to solve, and essentially what one can do, one can map this model to a percolation model on that shell. Yeah, so then it becomes easier. So it's a on-site percolation on this hypercube. Good. So that's a solution. So you can essentially calculate what is the probability of any side being on the shell of this energy shell. From there, you can do a simple sum algebra, and you can show that the crossover scale for this hypercube geometry without the correlation between energies will scale as 1 over L. Yeah. So previously I told you this log L. So this log L is difficult to find, but at least this 1 over L one can find in some limit. And indeed, if I show you the data, so this is the same data. So this is the connected cluster size as a function of, so this is as a function of this gamma parameter, which is just measures how strong your disorder is. And with increasing system size, it moves to the right. And as I told you, it should move as a 1 over L. So now it has been plotted as gamma times L, and we see a quite decent collapse of the data telling us that this shell geometry indeed fractures, at least show fracture crossover, and that has certain scaling. In this particular model is a 1/L scaling. Good. I don't have much time, so let me conclude. So I gave you two important kind of a concept. One is that there is something called potential energy shell, which has already been introduced in the ETH. Now I am telling you that potential energy shell, if it fragments in the occupation basis, the thermalization will be restricted, and that's kind of something that one can study. And in particular, in a model where the energies are non-correlated, which is called quantum random energy model, there it can be almost exactly solved. With this, let me thank you for your attention.
Thanks, Shomo, for maintaining time and for a very nice talk.
So,
Yeah, so we can have a couple of questions and we'll start from the first.
yeah. So can you put the slide for the entropy, please, which is way back? It very much looks like
That is Shannon entropy.
hadron entropy I talked about. If you treat
That is the Shannon entropy.
no, but it is in terms of wave function. Shannon is in terms of bits. Yeah, this one. So you remember what I? So this psi n is, if I look at the Fourier mode. No, I said Ek. It's identical if you interpret it that way. This is non-extensive, right? So this is non-extensive.
No, this is extensive because it's a log of the dimension of the Hilbert space, and if it is 2 to the power L, then it's a L times log 2. Yeah.
So for me, this number of modes, which is same as number of particles,
Right.
it becomes non-extensive. So does it ever decrease?
Yeah,
in
it-
some systems, this entropy.
Yeah, absolutely. So when the system is non-thermalizing and only occupying part of the Hilbert space, then it is a order 1 number. It will not scale with the volume of the system.
No, I didn't meant is function of time. Does it decrease ever? Like what we said.
Oh, it first goes up and goes down. Yeah, there are examples there. It can happen.
So that's like ordered system, isolated system getting ordered in time, right? It's like a.
Could be interpreted that way. I don't know. Yeah.
Okay, other question. Okay.
Just one question. So, when do the loops become important in this?
Time scales. So that loops becomes time scale.
Determines that time scale?
Oh, that's very difficult to estimate. So, no?
No,
No, it's very difficult to estimate. So, but think about the another thing. So, when I do these things, so let me just go to never wrote. So, e to the power iht. So, I can expand it, right? Delta e comes in the first order already. So, essentially, I'm looking at very small time, but this very small time for the disorder becomes pretty large actually. So, that's the one thing. But this, I don't know, but definitely it will kick in at some point of time, and the time scale is difficult to estimate.
Can it change the conclusion completely if you
My conclusion will not, because mine is geometry. So that's the thing. That's the whole debate about MBL, that there is some loops which could make things difficult. Yeah, sure.
So, is there any relation? So, you said the maximum connected cluster with the initial state.
Right,
If I take that ratio with the full Hilbert space,
right. That will go to 0.
that will go to 0 for
Yes.
large systems.
Yes, because the shell size you can calculate how it scales. This will scale with the linear of the L. So, and then
Even
the
without disorder, that will go to
it will no need to disorder. It's just a simple combination, and the whole Hilbert space is 2 to the power L. So it's a 1
So,
over.
is there any sort of prediction one can make based on this maximum cluster size? For example, how typical IPRs will scale with.
Yes, so, well, analytically I don't know, because it's a disordered, fully disordered interacting model.
So,
So,
you expect the cluster size grows, the IPR
yes,
falls.
IPR falls. Maybe in the quantum random energy model one can push it and make it some prediction, but not in this. I doubt that it will be possible.
So in like you consider a energy shell and you find out the number of states that are there in time. So like since you're also relating it to participation entropy and IPR, I was wondering, can it be a good measure for measuring designs, convergence to unitary designs? Like the psi we are talking about goes to the Haar random states, which will be anti-concentrated. So in that case, like, can we study an approximation to that in terms of like the shell that we are having, the number of states in that particular shell?
Yeah.
I thought, because you had the slide where you were saying that the connected, if you take out the connected states, you get to the same number of 0.71.
Right.
So, like, could we say that including those states are actually like a weaker thermalization that we are seeing?
asking longer questions, we postpone for.
Yeah, maybe I'll think about it. Yeah. Yeah.
Yes, so I just had this, so my understanding is a bit higher, so the number of red dots, and if you have more red dots, that changes the, it fragments the Hilbert space, yes?
Well, not the full Hilbert space. Is the one has to be careful here. It's a within the energy shell.
Okay, but are these fragments different because they are different energy?
There will be a distribution of fragments because of different configuration of
They are
disorder.
not the same fragment.
No. There is a distribution of fragments. Yeah, this is not exact. It's not protected by the symmetries or kinetic constraint or anything. It's kind of a weak fragmentation, if you wish. Yeah.
Okay, the last question, okay? Just be very quick.
Yeah.
Hi.
So I was asking, like, because the connectivity graph is so complicated, so you are just looking at the connection between the nodes at same energy. So because in the let's say
Similar energy, not exactly same energy. Yes.
because in the PhD model where we do this Fox-based graph, see, even though the graph is complicated, if you start from a state, it's just come back to the state.
Right. Right.
So how this complicated stuff, like we're saying that this is depends on that, like fragmentation. I think there are also other.
Oh, absolutely. The dynamics will depend on many other things. No, I'm not claiming that this is.
Like how this only the few connections between the nodes has same energy, similar energy, just characterize your IPR becomes like.
No,
I mean, how it is not depending on the other connection. Like,
no, it will depend. Eventually, it will. That's the whole. Yeah. So it will depend. At the very long time, it will depend. All the other connectivity will depend. That's the question of questions. Whether there will be time scales where the loops will matter, and then all this connectivity will come. But in the transient time, this is good enough to describe the dynamics. That's the point.
I think in the interest of time, we need to move on. So let's thank Shomya for a very nice talk.